I'm Stefano Foresti, and I'm the Director of Innovation at the School of Engineering at the University of California, Merced. And I'm here to talk to you about our Innovate to Grow program and the engineering capstone. And we have a project, the Riser Theory Designers, which is a project that was done for the Almond Board of California. And here there is Simon Truong, which is one of the team members of this project that is here to introduce the project and do question and answer. And so to talk about the program, the Innovate to Grow is an experiential learning program, and we have 3 classes. We have engineering capstone involving mechanical, civil, bioengineering, and materials, and then the software engineering for computer scientists. And these are classes where we use projects from partner organizations and industry. And so these teams work on these projects doing their classwork. And then there is engineering service learning that is a class more for the early years, for juniors and for sophomores. And it's with nonprofit organizations. So these classes have their own final exams as part of the Innovate to Grow event, which is an expo and judge competition with awards that is run every end of the semester. And this semester, it will be on Friday, May 14, 2021, from 11 to 2:30. So what is the value of this program in the undergraduate studies? Well, it's a win-win-win, a win for the students because the students have an opportunity to work on a real-world problem, to work for real clients, and therefore to have the ability to experience or put at work all what they learned, but also to learn the communication skills and the client skills that will make them complete and ready for the workplace. And also this program is going to give them opportunities because they have more exposure to industry. For the partners, this is a good program because it enables organizations to provide projects that they would like to have some solutions, but sometimes they don't have time to do it. You know, all organizations are full of problems, but they end up always working on the emergencies. And so we solicit projects that are always there waiting for a solution, and this way it's a way to anticipate and put some students at work. At the same time, some of the partners are using this program as a good way to expose students to their infrastructure, to their plans, and therefore to see how the students work. And it is a much better way to filter potential hires rather than looking at resumes. For UC Merced, it's a win because we have the opportunity to improve this educational program for engineers so that they are ready for the workplace and it provides them more opportunities. So at this point, I would like to introduce Simon, who is going to present the team and the work they did for the Riser program for the Almond Board of California. Simon?
Hello, I am Simon Truong, and I am a part of Team 22 of Fall 2020 Engineering Capstone, which worked on the Riser T for our client, the Almond Board of California. We are now graduates, and I am here to represent the work of all my teammates and address any questions. We organized the team with roles. Cody Costa was a project lead, Riley Cleaver, the team co-lead, Ruby Ferrolino, programming lead, Octavio Carranza, communications lead, Simon Truong, myself, financial lead. We called the team Riser T Redesigners as we were challenged to evaluate the current Riser T designs and to then recommend a new leak-proof option for the Almond Board of California. Next, we show the details of the problem, solution, and process. This video is a retouch version of our pre-recorded final capstone design review, as presented by all team members at Innovate to Grow Fall 2020.
The current design has issues such as the aging of fitting and tubing that leads to weak connection and leaks developed between locking collar and barbed slip connection. Over tightening of fitting leads to cracks in collars, barbs, the T-assembly, and hose adapter. The wear of washer in the threaded adapter also causes leakage. This issue causes water loss and can sometimes be undetected. And by reducing the amount of water loss caused by the leaks, we can help the almond board achieve one of their goals by reducing water loss.
The riser tee is used as the connection between the submain water line and the above-ground irrigation lines. Given this, our solution must have a watertight seal at each connection and must also be durable enough to withstand outdoor conditions and some accidental forces applied to the tee in order to reduce failure and save water. The constraints surrounding our solution include price, material, compatibility, and usability. The cost must be kept within margin of current units, which is about $4. The material we use to construct the tee must be UV resistant and non-toxic, as they're used in outdoors and for agricultural purposes. The tee also has to be compatible with the pipe sizes and connections that are currently used in irrigation systems. And finally, it must be easy to install and replace because when a failure occurs, an entire section of the irrigation system needs to be turned off, and they want to get the part replaced as quickly as possible to get the water running again. The objectives of our solution include minimizing the overall quantity of wastewater due to failure of these components, and also minimizing the cost of our alternative while still making improvements to longevity and durability. By reducing the frequency of failure and replacement of riser tees, we could greatly reduce waste of water. Our solution is similar to the current standard design with a few modifications. We decided to slightly change the geometry of the body to reinforce critical areas and to use a different material, high density polyethylene, to craft the tee in order to increase its durability. HDPE is stronger than standard polyethylene while also being impact, chemical, and weather resistant. We also chose to eliminate the twist tighten collar that secures the irrigation tubing and replace it with a metal crimping clamp. This would eliminate the possibility of over tightening the collar, which can cause damage to the tee. These clamps do require a tool for installation, but it's universal for all sizes. Here you can see how each component is connected. In the irrigation system, water flows from the below ground submain into the tee through a connection made by the threaded cap and sealed with a rubber washer. Once the water reaches the tee, it splits in either direction and out to the irrigation tubing. The tubing is fastened to the tee with a barb slip fitting and secured with a clamp in order to prevent the tubing from blowing off. To reduce the tee, high density polyethylene is heated and injected into a mold.
Moving on from our design schematics and our chosen solution overview, we get into a little bit of material simulation and performance testing. Our first test conducted was a flow simulation done in SolidWorks, and the purpose of this test was to evaluate whether the flow was laminar or turbulent. It was under great assumption that the flow would be turbulent considering the high pressure range the almond board usually works in. However, this test was further validity of that occurrence. In this case, our hypothesis was proven to be true, as we see a large swirling cyclonic behavior through the path of the water. In this case, distinguishing between laminar and turbulent flow is very important because now we know to evaluate for unsteady, chaotic behavior within the system. This may lead to things such as larger material stress is experienced, lots of vorticity, unexpected energy increases and decreases, and pressure gradients. Aside from flow animations, our simulation also provided us a few different graphics to interpret. If you look to the bottom left of the screen, we can see that this is the cut plot representing the pressure distribution inside of the tee. The largest pressure occurrence happens to be where the flow crashes vertically into the tee and begins its division. We see here, given that the almond board estimation was about 70 psi, that our maximum pressure here also resembles about 70 psi. As the flow divides, we see a little bit of a pressure decrease where it dips down to about 68. Not very much considering this is such a small system. Furthermore, the bottom right represents the vorticity of the fluid. As we previously discussed, vorticity is characteristic of turbulent flow, so this graph matched up very well with our findings. Finally, at the top right, we see the velocity distribution. Overall, we see a largest velocity of about 13 feet per second, and the minimum being 0 because of no slip condition along the boundary line of the material itself. This 13 feet per second, when calculated, gives us a turbulent Reynolds number as well, and even out through the arms, or at around 6 to 7 feet per second, also gives us a turbulent Reynolds number. At this point, we have determined that the flow is purely turbulent. Now, we need to examine what the maximum pressure is going to be felt by the body of the T. On the previous slide, we showed the cut plots of the pressure, the velocity, and the vorticity of the working fluid. And when examining our pressure, we saw a distribution of 70 pounds per square inch, or slightly under, depending on where you're looking in the T. However, when examining time dependencies, we need to include surge pressures. Surge pressures happen when there's a large change in flow rate as a valve is suddenly closed, or in some cases suddenly open, depending on which way the working fluid is traveling. For our evaluation, given that the maximum speed through the T was about 13 feet per second, we obtain an overall maximum pressure of 150 psi through the body. The next test we conducted was a static stress analysis. Knowing now that our maximum pressure was 150 psi, we wanted to gauge how well the material would perform and if there were any potential failures waiting in the system to happen. If we refer to the lower left image shown in this slide, the green shapes on the material itself are representative of fixtures, or where the material will not deform. Any red arrows mean that there is an external load applied. For those red arrows applied to the outside of the T-body, they represent any fixtures in the system, meaning interconnections between our subcomponents. This means the threaded cap may connect to the ground line, the washers may come in contact with any faces of the T itself, or the stainless steel clamps connecting to the irrigation lines. In any case, our internal loads are still 150 psi, as seen in our bottom right image, applied along the inner diameter of the T. When applying these loads, we reach a maximum von Mises stress of 1,736 psi.
Using our simulations, we also compared the performance of low density versus high density polyethylene, the material used in both current and our new designs respectively. In the test, the high density polyethylene performed better than the low with higher strength at yield and tensile modulus, giving us a factor of safety of 1.9 versus the previous 0.6, meaning a change in material would give us much more play when dealing with various stresses and strains the part can experience. Both plastics gain from being UV resistant. The high density variant, however, also has the added benefit of a higher melting point, which can prove beneficial when temperatures here in California can easily and frequently rise above 100 degrees in the summer, risking deformation from the intense heat. Here we have several angles of our T fully assembled, with the two clamps on each barb on the left and right, the threaded cap on the bottom surrounded by two rubber washers on either side, and the bottom hose line. Here's an exploded view to better differentiate each individual component, as well as highlight their place in the assembly. The larger washer higher in the assembly sits how it normally would in current market Ts within the threaded cap, but the smaller washer below it was added where the bottom valve meets the cap to add another layer of protection from washer failure. Our T is primarily composed of three materials: HDPE, or high-density polyethylene, EPDM rubber, and stainless steel. HDPE is used for both the T body and threaded cap, the washers are made of EPDM rubber, and the clamps are made of stainless steel. When selecting HDPE for our T, we were worried the plastic could degrade and leach chemicals into the water and later into the almonds. HDPE and other plastics will eventually degrade, and with the summer heat accelerating this, our concern only grew. But some research into the topic eased our minds, as degradation on that level would require an amount of time far beyond what we'd expect our tea to survive. Heat was also considered a minor issue, since cold water would constantly be moving through the tea, siphoning away heat from the plastic.
Cost of physical components. The T-body will cost 45 cents per unit, and this price was provided to us by Corey Broad from Jane's USA. Fortunately, the threaded caps are included in the T body, so there will be no additional cost for these. We found washers from a website called mcmaster.com, and the price for them from that vendor are 23 cents per unit. We also saw that mcmaster.com had pinch claps, and we have provided an image of how they look like. They are under the blue dollar symbol. These will cost us 46 cents per unit. Each of the T's will be using 2 washers and 2 clamps, which totals to $1.83 per assembled unit. Next, we have some of the assumptions we made when performing our cash flow, such as a MAR of 10%, an estimate of the amount of water lost by each broken T before repair, the labor costs associated with replacement, yearly water costs, an estimate of the percentage of failed T's, average orchard size, and an estimate for money back from recycling failed T's. We also performed our analysis based on the costs associated from a single orchard over 20 years, but we can update them later if anyone would like to see them, see the time frame or number of orchards increase. Also, we assumed a loan would need to be required to cover initial tooling costs for the manufacturing of the tea. With these assumptions, we came up with the net presence worths of $49,000 and $9,000 for the new and old teas, respectively. The new tea is considerably more expensive due to the high starting costs involved in creating a mold and tooling for injection molding. But in the time after the loan is paid off, the yearly cost of the new tea dropped below that of the current tea. In year 6 of our cash flow, the yearly cost of the new tea is $600, whereas the current design is $1,000. On behalf of the team, thanks to the Almond Board of California for the opportunity. Innovate to Grow and the Almond Board of California has allowed me to experience what it was like to use all the skills I have obtained throughout my college career and to use them to solve a real-world problem in an innovative and sustainable way with a team of diverse engineers, and I will always be thankful for all the wonderful faculty and students at UC Merced.
Thank you, Simon, for the presentation of the riser tea design and the work of your team. And here's the email of Simon if anyone will want to contact any of the team members. And about the Innovate to Grow program, so I would say that this was a very good example of how the projects in Innovate to Grow are. And I will solicit you to mark your calendar for Friday, May 14. From 11 o'clock to 2:30, we are hosting the Innovate to Grow of Spring 2021. We're going to have 30 projects in engineering and about 30 projects in software engineering. And I really welcome you to attend so you can have a visibility of our program. We are also looking for judges. You can register, and you find the registration on the website, innovatetogrow.ucmerced.edu. And if you are willing to judge, you can check the box of judging. And we are also soliciting projects for the next semesters, and there is a proposal submission in the website. Of course, if you have any questions, I'm here to answer them, and you can also write me an email. Thank you very much, and I look forward to seeing you at Innovate to Grow.